once registration is open. And with that, I will hand it over to Juliane Dunberg, who will chair our first session of talks this morning.
All right, hello everyone. Thanks everyone for being here. So in this first session, we first have one keynote talk and then we have shorter presentations. And so the keynote talk will be given by Anna Glerum, and it's on craton control on sediment-hosted metal deposits. So Anna, go ahead and share your screen.
Thank you. All right, how does that look?
Yep, great.
Perfect. Okay. Down. All right. Yeah, good to see you all again. Like Juliana said, I would like to talk about sediment-hosted metal deposits and how they are possibly controlled by cratons, their locations. And I'm doing this work with Sascha Brune, who's very sorry he can't be here today. He's also a geodynamic modeler working with Aspect and head of our section, and with Joe Magno, Philip Weiss, Sarah Gleason, and they are a geochemist and economic geologist. Now, I got into this topic because of the transition to a green society, a sustainable society, and green energy. And if you look, for example, at the United Nations Sustainable Development Goals that they designed for a prosperous future for both the people and the planet, you can see that many of the goals, they are underpinned by raw materials such as metals. Just look at industry and innovation, sustainable cities and communities, and in particular, affordable and clean energy. And here I put some figures that just highlight how the decarbonization, so stepping away from oil and gas in energy and transport sections, is resource intensive. So take, for example, an electric car, it takes about 5 to 6 more kilograms of metals compared to a carbon-fueled car. And for megawatt of wind energy, we need 15 tons of metals. It's a similar thing is demonstrated on the right here in terms of electricity. Let me just get a little spotlight. Yep, good. No, it's gone. Anyway, I show that the amount of copper equivalent you would need for a terawatt of electricity, and it's much higher for wind or solar powered electricity plants. However, the emission of carbon is practically zero with these technologies. But there are several challenges to this transition, and one is the circular economy is not a closed loop yet. So in the cycle from exploration to mining to production, collection, and recycling, we lose material every step of the way. And also materials are locked up for decades. Take a windmill, it will serve you several decades and the metals are locked up while it is in production. Another challenge is that the increase of demand will grow. And this is our 2020 demand for minerals. And these are the projections for 3 different scenarios. And if we go for a net zero carbon neutral 2050 scenario, then our demand for metals will increase 6 times. At the same time, there are many challenges like environmental, social, and governance challenges to getting these metals out of the ground and to processing them. And these are just a few examples of reported governance related risks, such as child labor and human rights abuses. And then finally, I'd like to note that many of the shallow deposits have been found, and we need to look for deeper deposits, which are harder to find and harder to mine. So I hope this convinces you that we need more metals and that we need to understand how their deposits are formed, not only on the reservoir scale, but also on a tectonic scale so that we can more easily find them. And these metal deposits that we're interested in, they are sediment-hosted, and they are of the clastic dominated type, so the CD type. They are zinc and lead mostly, and they are deposited in passive margins, rift basins, back arc basins, sag basins, all types of sedimentary basins. A second type is distinguished as the Mississippi Valley type. This is in platform carbonates, but we're focusing on the CD type here. So if you look at where these lead and zinc deposits occur around the world, and you plot them on a map of lithospheric thickness, this is converted from seismic tomography, and this was done by Hoggart et al. In 2020, you see that the location of these deposits corresponds with the transition from thin, so red, to thicker lithosphere, pretty much all around the globe. And if we zoom in on Australia over here, we can see that the deposits plot on this dashed line. And this dashed line is the 170-kilometer isocontour of lithospheric thickness. And this is what Hoggart et al. Define as the edge of cratons. And these are very old cratons, Archean Proterozoic age, and these deposits are also Proterozoic. So this is a configuration that has been around for a very long time. And then they gathered up the location of all deposits and plotted the total mass of metal against the distance from this LAB contour. And you can see that the majority of these metals occurs within 200 kilometers of the edge of cratons. And that's a lot higher than what you would get if you would just plot random locations. So it seems there is a relation between craton edges and deposits, but why? Well, the rift dynamics, the large scale rift dynamics, they control the parameters of metal leaching and metal deposition. So for example, rifting leads to high temperatures and high heat flows. And this is important for fluid flow and metal leaching. Rifting leads to faults, and these provide fluid pathways. Sediment from the rift shoulders gets turned into source rock in the basins. Seawater provides fluids, sediments, and sulfates that are also needed, and then organic rich sediments, they form the host rock. So there is a geodynamic control in the circumstances needed for metal leaching and transport and deposition. And this geodynamic control and this rifting process is something we can model, and that's what I do. And obviously I use Aspect, but I use it coupled to a surface processes code called Fastscape. This is created by Brown and Willett in 2013 and extended by Yuan et al. And the coupling was made by Derek Neuhardt, former PhD student in our group. And this means that sedimentary processes such as river incision, hill slope diffusion, and marine transport and deposition of sediments are included in the modeling. So I tried to graphically represent how this coupling happens. Let me see. So if we imagine this big arrow to be the, move this out of the way, to be an aspect time step cycle, then at the beginning of a new time step aspect, let's say it's a 2D model for 2D vertical model, aspect gives its horizontal and its vertical velocity to Fastscape, and Fastscape works in the horizontal plane, and it uses the vertical velocity to uplift or subside the surface and the horizontal velocity to advect the surface, and then it applies at the same time in several time steps. It solves the equations that govern the other processes, such as river incision. Then it returns the new surface to Aspect, and Aspect determines the difference from the new surface and the old surface and transforms that into a velocity. And this mesh velocity is used to also determine the mesh velocity in the internal mesh, not just at the surface. And then Aspect continues its cycle and solves for temperature, pressure, and velocity, etc., and starts again. Now, there are two things that I added here, and that is that aspect includes some pelagic sediment rain. So this is just sediment from the water column in the marine domain sinking before Fastscape takes over. And Fastscape also returns a grain size of the continental sediment. So they can either be coarse or they can be fine grained. So let's say they can be sand or they can be silt. Now, a typical setup of the models I've been running looks like this. We have the 2D vertical aspect model and the horizontal Fastscape model on top. So it's like a T model. And it's 300 by 700 kilometers, yes. And the lithosphere varies from 120 kilometers, so normal continental lithosphere, to 200 kilometers, mimicking a craton. And I use mesh refinement so that we can resolve the sediments, and this maximum resolution at the top is like 300 meters. And then the driving force is actually the extension that I prescribe on the left boundary. And the bottom is an open boundary where material can move in or out in response to what's happening inside. The surface is coupled to Fastscape. Fastscape's initial topography is just some random noise between several meters. Yeah, and then what I vary in these models is the initial distance between the rift seed, so what I use to localize deformation in the model, and the edge of the craton. And what I use to localize deformation in the center is both a slightly thinner lithosphere, a slightly thicker lower crust, but also these bluish thingies that is like random plastic strain, so random noise, because we don't know what the structure of the lithosphere was in the Proterozoic. So we mimic different configurations, different heterogeneity by using this random noise strain. So there I vary the amplitude and the seed of the strain. And then I run the model for 25 million years. Okay, so this leads to a parameter space that's governed by the distances between the rift seed and the cratons, and then the characteristics of the initial strain. And then this is the results of a typical model. And here the initial distance between the rift and the craton, as you can see, is 50 kilometers. And at the bottom, it's aspect, and at the top, I show Fastscape. And we can see that after 0.5 million years, two border folds have formed. But the one dipping towards the craton is strongest, and this turns out to be quite important. We have formed like a below sea level basin in Fastscape. And then if we move forward through time, after 5 million years, we see we have developed rift shoulders that are being eroded by rivers, creating these valleys. And in aspect, we see we have two sedimentary basins already, where one is bordered by an inactive fold. So here we only see plastic strain, but not active high strain rates, such as over here. And the asthenosphere is upwelling, and then over time, the center of deformation, I will show zoom-ins later, the center of deformation migrates towards the craton side, and actually the asthenosphere sort of eating away at the crust. The top topography becomes quite smooth, it's being eroded away, and that continues up to 25 million years. Now, if you remember this, the rift shoulders that formed, I plotted the topography over time here for 3 different models, and time is indicated by the colors of these lines. So this pink is at 25 million years. And you can see that for different initial distances between rift and craton, there is this distinct asymmetry in the height of the rift shoulders that disappears for greater distances. What you can also see is that there is a wide margin a wide margin on the left here for the center graph, and a narrow margin, so very steep and narrow on the right. And this corresponds to the direction of the dip of this initial shear zone in the model results. And if I just count the models in each for each initial distance, so there were 9 different configurations of initial strain, then if the distances are small, then all the craton margins are narrow. So all the margins, passive margins on the side of the craton, they are narrow. But if I go to greater distances, then they're more or less 50-50. And this control on the margin width by craton was also found by Andres Martinez in 2016, where he shows that the margin width for the craton margin and the opposite margin varies greatly if the craton is quite close. Now, the first thing I then looked at was the amount of sediment that is created, because the sediments will provide the location of the ore deposits and the source of the ores. So I looked at whether there's how the amount of sediment, the total amount of sediment develops over time, and I plotted that for the different distances. And you can see that only for cratons further than 150 kilometers away, there is a distinct increase in the amount of sediments. This is mostly due to this jump at around 3 million years that I think is related to a sediment deposition event on land, but I haven't fully figured that out yet. Now, within these sediments, we have the hydrothermal processes. And for our ores, it's this hydrothermal ore formation, and this considers fluids flowing through large areas with lower densities of metals and leaching the metals from the source rock. And then somehow these fluids are focused and they transport their metals away from the source rock. And one of these focusing elements can be faults, which are highly permeable. And then the fluids come to the deposition site, something changes and lets them drop the metals, and then they go on and live their life. And the forces contributing to this are heat coming from the interior of the mantle. So in the rift system, it's the heat coming from the rising stenosphere, but also a topographic head and compaction are important. Now, the solubility of the fluid, so the amount of metals that they can hold and transport, depends on several things: temperature, salinity, pH, redox potential. But for our system, temperature is the main controlling variable. And on the right, I just show an example of how the lead concentration in a fluid changes if you decrease the temperature. So it decreases with lower temperatures. So we define our source rock as sand with temperatures higher than 250 degrees Celsius. So sand is quite permeable, so the fluids can flow through and pick up metals, but it needs to be hot enough so that their solubility is high enough. And then the host are marine sediments with temperatures lower than 150 degrees sediments. And then we now look at the zoom in of the model of 50 by 400 kilometers. And here I color code the sediments. You'll mostly see sand, orange stuff, but there are marine sediments as well. They are purple. And when the sand is warm enough, I color it dark green. When the purple pelagic sediments are cold enough, they become light green. So green is good. Yes. So if we then move through time, again, we have the two basins that form, and you can already see some host material forming here close to shore and in the second basin, third basin. And then over time, rift migrates, craton ward. We have long stretches of pelagic sediments at low temperatures, but hardly any source material forming. There is a tiny bit over here, not a lot. And this is for 50-kilometer distance between the rift and the craton. Now, if I then plot one model out of each suite for each distance, And we can see this clear trend that the further the craton is, the more source rock forms. But once it's like 200 kilometers or more, that doesn't really make a difference anymore. We can do the same thing for the amount of host rock. And here I plot all the 9 different strain configurations for 50-kilometer initial distance, so close craton. And you can see that the model results for each model, results are very similar. And that after about 10 million years, there's this stable increase. But for 150 kilometers and more of initial distance between the rift and the craton, we see 2 trends. And these trends represent a wide craton margin, so a narrow opposite margin, and a narrow craton margin. So for 200 kilometers or no craton, we see similar thing. But if I plot the narrow craton margin models of each distance, then again, we see a trend. And the closer the craton is, the more host rock we form. And this is exactly opposite to the trend with the source rock. So that's kind of counterintuitive. Then finally, we need a focusing event like a fault to happen to bring the fluids from the source rock to the host rock and to focus the metal concentration. So here I plot the area of source and host rock that is also being faulted. And by faulted, I mean it has a strain rate that is higher than 5 to the minus 15, 5 to the power minus 15, almost 1 over second. Yeah. And again, this increases the further the craton is. Now, what is actually as important is to have source and host rock together in the same basin. So now I don't only count, I added a column to the table, and I count also whether source and host co-occur in a basin. And you can see that for close distances, they don't. But then the further the craton comes, it's again, sort of 50-50, but it corresponds to the craton side being the wide margin and not the narrow margin. So I will show you some snapshots of the models to illustrate these situations. So the top figure is the basin for a 50-kilometer distance between the rift and the craton. And we can see, again, we have this very large, very wide opposite margin and quite a narrow margin on the cratonic side. And there has formed dark green, so source area, and that is now later on being faulted because the locus of deformation is migrating into this basin. However, for this larger initial distance, we see this similar thing happening on the other side, so on the opposite margin, which is now the narrow margin. But here actually source and host rock have formed, and then there is a fault that connects the two. Then a third situation occurs in this model. It's also for an initial 150-kilometer distance, but here the source and the host rock actually formed in a basin that was actively faulting, and then new faults formed and connected the source and the host rock. And then the final example for a 200-kilometer distance, we see we have a larger area of source and host rock that is then later being faulted, but again in the opposite margin. And I just show a zoom in here where you can see how the fault connects the two areas. Now, if you then measure the distance between this between this possible location for the formation of an ore deposit, right, and the edge of the craton, this is 400 kilometers. So this is more than what, according to observations, the majority of the deposits is located in, which was 200 kilometers. So these observations are still a bit of a conundrum to explain, but there is some hope on the other side where we see this basin that has like a continuous sort of cap of host rock, a tiny bit of source rock, but no active faults. But actually, if you look at the Carpinteria zinc belt in Australia, the history is debated, but also it's most likely that history consisted of periods of extension and compression, fault reactivation, new faults being created. So it could very well be that this fault was reactivated or new faults on smaller scales form that could lead to favorable conditions for metal deposit formation. So to summarize what I just told you, I used a couple geodynamic and surface processes modeling to look at how favorable conditions form for metal deposits. And we found that a craton determines the asymmetry when it's less than asymmetry of the margins when it's less than 150 kilometers away. And this is dictated by the direction of the initial cross-lithospheric shear zone, which points in the direction of the craton. Also, most solar source rock occurs for more than 200 or more kilometers between the initial rift and craton, but most host rock occurs for a closer craton. And then the co-occurrence of source and host rock occurs mostly in the narrow margin, and it doesn't matter if that's like the craton side or the opposite side. And then the co-occurrence of source and host and faults in one subbasin close to a craton is very rare, and that's unicorn that we're looking for. So next steps are to compare the modeling results more closely to the Carpinteria zinc belt, where my colleagues have worked, and we have lots of observations, and then hopefully extract some characteristics of favorable plays, so favorable conditions such as rift stage, sediment thickness, initial distance to the craton, etc., for the formation of these deposits. And then maybe we can create fault maps of favorable locations. At the same time, I'm working on one-way coupling the aspect fastscape models to a hydrothermal code. This code is called CSMP++, and it can model actual fluid flow, metal leaching, metal transport, metal deposition. So as a proof of concept, I showed these figures over here, and the top figure A shows what I cut out of the aspect model results and fed into CSMP++. So I take aspect solutions for temperature, pressure, vertical heat flow, composition, topography, the mesh, basically. I take all of those and I feed it to CSMP. And then CSMP converts that into a permeability. So, I also take the strain rate. So high strain rate areas are identified as faults and are then given a high permeability. And then dependent on the sediment type, it gets a different permeability. In the basement, it's impermeable. And then you can see that over time, so figures B to D, the temperature, so that came initially from aspect, the temperature field evolves based on what the fluids do. And you can see that the changes in the temperature are greatest around the faults, which are outlined by these green lines. And then there's this zoom in the middle where we start off with a high temperature area, and that is being cooled by the cold and saline fluids coming from the top. And then you can also see warmer fluids traveling back up. So I'll continue working on this, and then hopefully we can, for example, use it to infirm the cooling effect of the fluids that are now missing in my aspect models by comparing them to these hydrothermal models. And then finally, the end goal is to model across all the scales, so from the geodynamic to the hydrothermal system scale, the formation of these metal deposits, and then hopefully improve prospectivity mapping so that we can keep building windmills. Thank you.